Hello guys, you're welcome back to my channel, and today we are going to talk about the classification of second order partial differential equations. And if you already like the content of my channel, just leave a like on my videos and then subscribe to my channel as well. So let's just get straight into it. And why do we want to talk about classification of second order partial differential equations? So there are three main second order partial differential equations, of which all other second order partial differential equations follow. Okay, so we have the wave equation, we have the Laplace equation, and then we have the diffusion equation. Okay, so every second order differential equation, partial differential equation looks like either of these. Okay, and the reason why we are doing this classification is that if you know the class of a second order partial differential equation, you can solve it as the corresponding known equation. Okay, so for instance, if you get to know that a second order partial differential equation is hyperbolic, then you can solve it as the wave equation. If it is elliptic, you can solve it as you're solving the Laplace equation. If it is parabolic, you can solve it as solving the diffusion equation. Okay, yeah, so these second order differential equations are based on the kind of the operator that joins the second order term. So in the wave equation, uxx and uyy are joined with a negative sign. So keep that in mind. The Laplace equation, you have uxx and uy, the higher, the second order terms, the uxx, uyy, they are joined by, a positive. And when you come to the differential equation, you just have one term, that's just the uxx. Okay, you don't, so it's more like there's a zero connecting uxx and uyy. So keep that in mind. For wave equation, you have a negative. For Laplace equation, you have a positive. For diffusion equation, you have a zero, operator joining the higher order terms. So keep that in mind. So let me write that here. So for wave equation, and that happens to be the hyperbolic equation, right? You have a negative sign. For Laplace, you have a positive sign. So you get to know why I'm writing all these things. For diffusion, is zero. Okay, so we have to know that. So if I'm given any partial differential equation, so let's generally write a partial differential equation. Let me check my notes real quick. Okay, so given the second order differential equation, I have a11, uxx plus 2a12. I'm using 2 for a reason. It could be any number. 2xy plus a22 uyy plus 2ux, and the first order terms and some constant, let's say an whatever, it's gonna be 0. Okay, so this is a second order partial differential equation. Even though you have first order terms and then you have constants, this is still a second order partial differential equation because the highest order term is a second order term. Okay, so our point of interest will always be the second order terms. Okay, so those are the terms you're interested in. So all these terms, we don't really care about them. So I'm going to rewrite that. I'm going to have a u11 plus 2 a12 uxy plus a22 uyy plus the other terms which we are not interested in to be equal to 0. Okay, and then what we're going to do here is to write the coefficients of these second order terms as in a symmetric matrix form. Okay, and then we know how to do that from linear algebra. So that matrix, I'm going to call it matrix A. It's supposed to be a symmetric matrix. So the diagonals are just going to be A11, A22. and then the non-diagonals are going to be half of whatever you have here. Okay, so all the uxy, you can have uxy, uxz, u, yz. You divide the coefficients by 2, and then you put them to, you distribute them over the, the non-diagonals. So here's going to be a12 and a21, but since this is supposed to be a symmetric matrix, it's just going to be the same a12, right? Good. Then what we're going to do is to find the eigenvalues of this. So that's going to be a11 minus lambda, a12, a12, a22 minus lambda, and that's supposed to be equal to 0 since you're finding eigenvalues. So we're going to have a11 minus lambda multiplying a22 minus lambda minus a12 squared. That should be equal to 0. You simplify this, you're going to have lambda squared minus a11 plus a22, I guess, lambda, then plus a11, a12, a22 minus a12 squared. That should be equal to 0, right? I'm so sure. Okay, so now this is very important. Okay, so now here's this is where the trick comes in. So what we're going to do is that, this can be, this is actually the form of any quadratic, right? So, this is going to be the sum of roots. Okay. And this is going to be the product of roots. Okay. So now we are interested in the products of roots. The product of roots. So the eigenvalues, the products of these eigenvalues are giving you that. Okay. So I'm going to call that product delta. That's going to be a11, a22 minus a12 squared. Now this is what we are interested in. Okay. Because this is going to contribute, or that's going to tell us the sign we are having here. Okay. So we know that if the sign is negative, then you have a hyperbolic second order partial differential equation. If it's positive, you have an elliptic one. If it is 0, you have a parabolic one. And the sign is determined by this product. Okay. So it means that if this delta is greater than 0, what happens? It means that you have a positive, sign joining the second order terms. And if that happens, if you have a positive one, we have an elliptic second order PDE, right? PDE. If this is equal to 0, what happens? If it is equal to 0, we have, it looks like the diffusion equation. And what is the diffusion equation? It is a parabolic second order so we have a parabolic second order PDE, and if delta is less than 0, you're gonna have a hyperbolic second order PDE. Okay. Yes. So the reason why we are using this determinant form or the eigenvalue form is that this can be generalized to a 4x4 symmetric matrix. You can have even a 5x5 symmetric matrix, and you can still classify it using this analogy, these three statements here. Okay. Yes. So in the next video, we're going to see some examples of classifications. We're going to start off with a 2x2 symmetric matrix, and then we're going to classify that PDE. Then we move on to a 3x3 symmetric matrix, and then see how we are going to classify all these things. Okay, it's very simple. And let me go back, let me explain, let me mention why we are doing classifications all over again. We do classifications so that we get to know what type or what class of second order equation is. And once we get to know what class it is, right, we can solve the second order PDE as the known form of that class of second order PDE. So for instance, if you find out that it's a hyperbolic second order PDE, you can solve it as you're solving the wave equation, which you're going to see in some videos to come. If it is elliptic, you can solve it as you're solving the Laplace equation, which you're going to also see. And if it's parabolic, you can solve it as the diffusion equation. All right, so see you in the next video. Bye bye.